We now show a different equivalence between Delaunay triangulation. We show that Delaunay triangulation can be obtained from a convex hull of a three-dimensional set of points. To get there, first we have to make some basic observation regarding an equation of a circle. Imagine I have a circle with center at point AB and with radius r. The set of points inside the circle can be written using the following inequality. What this inequality mean is that any point xy in the planes that obeys this inequality is inside the circle. So in particular, if I pick a point here of coordinate x and y, and if it's true that x squared plus x minus a squared plus y minus b squared is less than or equal to r, then this point has to be inside the circle. By expanding this inequality, we get here, and finally we get here. So now we could use the technique that is known in computational geometry as linearization. In particular, we have an inequality that is not a linear function because we have the exponent 2 here, and we can turn it into a linear function by adding some extra variables. We rename this part z, which will turn this part of the equation into a linear function. Notice that this right hand side is not really part of linearization because this is a constant, because we have a fixed circle, right? So a, b, and r are just constant. I can just relabel all of these things as c. So now I have this linear function. So z minus 2 times ax minus 2 times by less than or equals c. In three-dimensional space, or in three-dimensional Cartesian space, where I have three coordinates x, y, and z, this describes a linear function. This will be a hyperplane. Okay? And the only assumption I have made here is that z equals x squared plus b. What does these two imply? It implies the following. If I take this equation of this half space and the assumption that z equals x squared plus b, then this would solve to the set of points inside a circle based on what we observed. What does this mean geometrically? So the equality z equals x squared plus y squared describes a parabola. So this is the best representation of parabola that I could draw. Okay. Any point on the surface of this parabola has its z coordinate equals x squared plus y squared. As a result, what this means is that if I take the set of points on the parabola and given a hyperplane of this form, if I intersect them, then the set of points that are on the parabola but they are below this hyperplane will form a circle, or in other words, their projection onto the xy plane will form a circle. That is what we get by removing z and just dealing with x and y. Right, so I will get this picture where this piece of the parabola is sliced off using a hyperplane, and once I project it, I get a circle in the xy coordinate. So based on this, I could do the following. I could map a set of input points. So imagine I have a set of input points that I would like to find their Delaunay triangulation. I map them to a set of three-dimensional points by adding a third coordinate, which is given like this. What this does is that it lifts every point onto the surface of this parabola, because the z coordinate of the points equals their x coordinate squared plus their y coordinate squared. Now I'm going to use the empty circle property of the Delaunay triangulation. Remember that the 3 points form a Delaunay triangle, or form a triangle in a Delaunay triangulation, if and only if the circle that goes through them is empty. Based on what we have observed, the equation of the circle, or the set of points inside the circle, corresponds to the set of points that are below a hyperplane and that are on the surface of the parabola. Remember that all my input points are now on the surface of the parabola. So what does it mean for a circle that goes through 3 points to be empty? It means that all the other points that are on the parabola are above this hyperplane. Okay? As a result, this triangle must be a face of a convex hull, because the hyperplane that goes through these 3 points does not have any point below it. In other words, this is a face of the lower hull of these set of points. So a more probably pleasing and accurate picture will look something like this, that given a set of points, if I lift them using this lifting map, I get a set of points on the parabola. If I can compute a convex hull, or in fact a lower hull, and if I then project the lower hull down to the 2D, I will get the Delaunay triangulation. Just one minor remark, this reduction is only one way. In other words, not every 3D convex hull is a Delaunay triangulation. In other words, if you have some 3D convex hull and have to project it down to 2D, you may not get a Delaunay triangulation. This shows that computing 3D convex hull is at least as hard as Delaunay triangulation. Or in other words, computing Delaunay triangulation is easier than a 3D convex hull. If you have an algorithm that can solve 3D convex hull, you can have an algorithm that solves Delaunay triangulation, but the reverse is not necessarily true.